Section. Introduction. Let's start by discussing the importance of initializing the weights in neural networks. This process is key to optimizing these networks, as it helps the model converge and avoids problems like the gradient disappearing. Two well-known techniques for this are Xavier initialization and K-means initialization, which are commonly used in modern deep learning libraries like PyTorch. These methods were designed for training neural networks from a random starting point, which was the standard practice at the time. However, things have changed. Now, we have a wide range of pre-trained models at our disposal, thanks to the collective efforts of the community. These models have been trained on large datasets like ImageNet 21K and LAION5B and have often been fine-tuned by experts. As a result, it's usually more efficient to fine-tune these pre-trained models rather than training new models from scratch. But there's a catch. These pre-trained models can be quite resource-intensive, which can make them difficult to use in situations where resources are limited, such as on mobile devices. Even the smallest pre-trained models can be considered large in certain contexts. For instance, the smallest pre-trained transformer models provided by masked autoencoders, MAE, and CLIP, known as VitBase, have 80 million parameters. This is too large for applications on edge devices, and the smallest Llama model is even larger, with 7 billion parameters. Given the lack of small pre-trained models, developers often have to train models from scratch on their target datasets. This means they miss out on the opportunity to use large pre-trained models, which have been trained on extensive data. In this work, we address this problem by introducing a method for initializing the weights of small models using large pre-trained models. We call this method weight selection, and it involves choosing a subset of weights from a pre-trained model to initialize a smaller model. This allows the knowledge gained by the large model to be transferred to the small model through its weights. Thanks to the modular design of modern neural networks, weight selection involves just 3 simple steps: layer selection, component mapping, and element selection. This method can be applied to any smaller model within the same model family as the large model. Using weight selection to initialize a small model is straightforward and doesn't add any extra computational cost compared to training from scratch. It could also be useful for training large models, for example, initializing a Llama 7B model with trained weights from a Llama 30B model. We've applied weight selection to train small models on image classification datasets of different scales. We've found that it significantly improves accuracy across datasets and models compared to the baseline. Weight selection also substantially reduces the training time required to achieve the same level of accuracy. Furthermore, it can be used alongside another popular method for transferring knowledge from large models, known as knowledge distillation. We believe that weight selection can be a general technique for training small models. Our work also encourages further research on using pre-trained models for efficient deployment. Now, let's talk about related work in this field. Weight initialization is a crucial part of model training. Some methods maintain constant variance by setting the initial values of the weights using a normal distribution, which helps prevent the gradient from vanishing or exploding. Other methods modify this approach to adapt to ReLU activations, or use orthogonality in weight matrices to keep the gradient from vanishing or exploding. Some methods use external sources of knowledge, like data distribution or unsupervised training, to initialize neural networks. For example, data-dependent initialization can be obtained from performing K-means clustering or PCA on the training dataset. Transfer learning is a common framework for using model weights pre-trained from large-scale data. The model architecture is maintained and the model is fine-tuned on specific downstream tasks. Knowledge distillation involves training a smaller student model to approximate the output of a larger teacher model. This allows the student model to maintain the performance of the teacher while being computationally efficient. Another alternative approach for using pre-trained models is through weight pruning, which involves removing less significant weights from the model, making it more efficient without significantly compromising performance. Some methods transform parameters of a large network to a smaller one through learnable linear layers using knowledge distillation to match block outputs. Others create smaller models by initializing with a subset of layers from a pre-trained BERT. This method requires the smaller model to have the same width as the teacher's. Some methods borrow weights from existing convolutional networks to initialize novel convolutional neural networks. Others transform weights from smaller networks as an effective initialization for larger models to accelerate convergence. Some methods initialize convolutional layers with a Gaussian distribution according to the pre-trained model's covariance, or initialize self-attention layers according to observed diagonal patterns from pre-trained VITs. These methods use statistics from, but do not directly utilize, pre-trained parameters. The concurrent work applies structured pruning to reduce existing large language models to their smaller versions and uses the pruned result as an initialization. In contrast, weight selection directly utilizes pre-trained parameters, does not require extra computation, and is suitable for initializing any smaller variants of the pre-trained model. Section Summary. The initialization of neural network weights is crucial for optimization, and two popular techniques are Xavier initialization and K-means initialization. However, with the availability of pre-trained models, fine-tuning from these models is preferred over training from scratch. To address the resource constraints of large pre-trained models, we propose weight selection, where a subset of weights from a large model is used to initialize a smaller model. This method allows for knowledge transfer from the large model to the small model and improves accuracy while reducing training time. Section. Weight selection. We aim to create a smaller model from a pre-existing one, which we'll refer to as the teacher model. The smaller model is known as the student. The process involves 3 steps: layer selection, component mapping, and element selection. Firstly, we select layers from the teacher model to use in the student model. The method of selection varies depending on the architecture of the neural network. For networks with a consistent design throughout, like VIT and MLP mixer, we simply choose the first n layers, where n is the number of layers in the student model. For networks with a hierarchical structure, like convenext, we apply the same method but at each individual stage. Alternatively, we can select layers at regular intervals throughout the teacher model. Our research suggests that selecting the first n layers is the best approach. Next, we map components between the student and teacher models. Since modern neural networks often use a modular design, the layers in models from the same family have the same components, just in different sizes. This makes it easy to match corresponding components between the two models. Finally, we initialize the student's components using the corresponding components from the teacher model. The default method for this is uniform selection, where we select elements at regular intervals from the teacher's tensor. We'll discuss this and other methods in more detail shortly. We've explored several methods for element selection. The goal is to select a subset of elements from the teacher's weight tensor to initialize the student's weight tensor. We've found that maintaining consistency in the selection process is key to achieving good performance. We recommend using uniform selection as the default method. In uniform selection, we select evenly spaced slices from each dimension of the teacher's weight tensor. For example, to initialize a 2x3 linear layer with a 4x6 linear layer, we would select the first and third slice along the first dimension, and the first, third, and fifth slice along the second dimension. This method is particularly effective for architectures with grouped components, as it ensures information from all groups is included. Another method is consecutive selection, where we select consecutive slices from each dimension of the teacher's weight tensor. This method is equivalent to uniform selection for architectures without grouped components. We also considered random selection, where we select a random set of slices from each dimension of the teacher's weight tensor. We found that it's important to select the same indices for all weight matrices to achieve the best performance. This is because it preserves the operations of neurons added in the teacher model in the student model. Uniform and consecutive selection inherently preserve this consistency. Finally, we examined random selection without consistency, where we select random slices from each dimension of the teacher's weight tensor without needing to select the same indices for every weight tensor. This method was used to test the importance of consistency. Section Summary. Weight selection is a process of initializing a smaller model using a pre-trained model as a teacher. It involves 3 steps: layer selection, component mapping, and element selection. Layer selection involves choosing layers from the teacher model to initialize the student model. Component mapping establishes a one-to-one mapping between the components of the two models. Element selection involves selecting subsets of the teacher's weight tensor to initialize the corresponding components in the student model. Different methods for element selection, such as uniform selection and consecutive selection, are discussed, with uniform selection being proposed as the default method. Section. Experiments. We conducted a series of experiments to evaluate the effectiveness of weight selection in image classification tasks. We used 9 different datasets for this purpose, including ImageNet 1K, CIFAR10, CIFAR100, STL10, Food 101, DTD, SVHN, and Eurosat. These datasets vary in size, with the smallest containing 5,000 images and the largest containing 1.3 million images. We used 2 models for our experiments, VIT-T16 and ConveNeXt-F. These models were trained using pre-trained versions of VIT-S16 and ConveNeXt-T, respectively. We obtained the weights for these pre-trained models from their respective sources. Our training process followed the ConveNeXt training recipe, with some adjustments to the batch size, learning rate, and stochastic depth rate to suit the different datasets. We ensured a fair comparison by using the same set of hyperparameters for training with weight selection as we did for training with random initialization. For the random initialization baseline, we used the default initialization from the TIM library, a popular computer vision library known for its reliable reproducibility. This default initialization uses a truncated normal distribution with a standard deviation of 0.02 for linear and convolution layers. This type of distribution is commonly used in the development of modern neural networks because it clips initialization values. Our results showed that weight selection consistently improved test accuracy across all 9 image classification datasets, especially for smaller datasets. This is particularly noteworthy because it addresses the well-known challenge of training VIT on small datasets. Both models benefited from weight selection early in the training process and maintained this advantage throughout. We also compared weight selection and its variance with 2 widely used initialization methods, Xavier initialization and K-means initialization. Our results showed that all variants of weight selection performed significantly better than these classic initialization methods. We found that consistency is crucial for weight selection to achieve its best performance. Uniform selection, consecutive selection, and random selection with consistency all achieved similar levels of performance. When we removed consistency, we observed a sharp drop in performance. We also explored the compatibility of weight selection with knowledge distillation, another popular method for transferring knowledge from pre-trained models. We evaluated the performance of combining weight selection with 2 different approaches in knowledge distillation: logit-based distillation and feature-based distillation. Logit-based distillation uses KL divergence as the loss function for matching the output probabilities of the student and teacher models. This requires the teacher to be trained on the same dataset as the student. For feature-based distillation, we used an MLP to project the student's output to the teacher's embedding dimension, and used L1 loss to match the projected student's output and teacher's output. Our results showed that weight selection and knowledge distillation are compatible and can be used together effectively. Using weight selection alone produced better results than using either logit-based distillation or feature-based distillation alone. However, the combination of weight selection and knowledge distillation produced the best results, boosting accuracies to 76.0% on ImageNet 1K and 83.9% on CIFAR100. This confirms the usefulness of weight selection as an independent technique and its compatibility with knowledge distillation. Section Summary. The authors conducted experiments on 9 image classification datasets, including ImageNet 1K, CIFAR10, CIFAR100, STL10, Food 101, DTD, SVHN, and Eurosat, to evaluate weight selection. They used VIT-T16 and ConveNeXt-F models, with ImageNet 21K pre-trained VIT-S16 and ConveNeXt-T as their teachers, and obtained weights from these pre-trained models. Weight selection consistently improved test accuracy, especially for smaller datasets, and addressed the challenge of training VIT on small datasets. Weight selection also showed compatibility with knowledge distillation, producing better results when combined with logit-based or feature-based distillation. Section. Analysis. In this section, we delve into a thorough examination of how we choose weights. Unless stated otherwise, we'll use a standard setting for comparison, which involves starting with a vision transformer T, VIT-T, that has been uniformly selected from a pre-trained vision transformer S, VIT-S, on ImageNet 21K. This model is then trained and evaluated on the CIFAR100 dataset. We discovered that choosing weights wisely can significantly cut down on training time. We measured this by training the VIT-T with different weight selections for varying numbers of epochs. We found that with the right weight selection, we could achieve the same performance on the CIF-AR100 dataset with only a third of the epochs compared to starting from scratch. We also compared our method with transfer learning. We conducted experiments to determine how much training would be needed to match the accuracy of our weight selection method. We found that it would take 60 epochs of pre-training on ImageNet 1K to achieve the same performance on CIF-AR100. This means that our weight selection method is over 6 times faster than achieving the same performance with pre-training, and we don't even need to access the dataset used for pre-training. We also looked at the impact of using different pre-trained models for weight selection. We found that models with supervised pre-training were the best teachers. We tested the performance of VIT-B as a teacher under different pre-training regimes and found that starting with pre-trained weights consistently outperformed starting from scratch. The ImageNet 21K pre-trained teacher provided the most effective initialization. We also compared two methods of layer selection, selecting the first N layers and selecting layers uniformly. We found that selecting the first N layers performed better, likely because these layers are naturally closer to input processing and provide a more effective initialization for smaller models. We also compared our method with pruning, a technique used to reduce the size of neural networks. We found that our method outperformed both structured and unstructured pruning methods. However, we noted that our setting is different from neural network pruning, which typically only prunes within residual blocks for networks with residual connections. We found that starting with a teacher of a similar size produced better results. A larger teacher means that a higher percentage of parameters will be discarded, which leads to more information loss during weight selection. We used linear probing to directly measure the raw model's ability as a feature extractor, which can be a good indicator of the quality of initialization. We found that without any training, our weight selection method performed significantly better than starting from scratch in producing features. We also conducted ablation studies on VIT-T to understand the influence of distinct model components on performance. We found that excluding any component from initialization led to substantial drops in accuracy for all datasets, confirming that initializing with all components from pre-trained models is necessary. We also assessed whether our weight selection method remains beneficial for extended training durations. We found that our method continues to provide an advantage even under extended training durations. Finally, we compared our method with mimetic initialization, which uses the diagonal properties observed in the pre-trained self-attention layers weights to initialize vision transformers. We found that by directly utilizing pre-trained parameters, our weight selection method outperformed mimetic initialization by a large margin.